Probably the most documented homebrew project in ham radio is building an antenna. So why make yet another video on the subject? Well, that's a good question. But what I think this video presents is a reproducible approach to build a 4-element 2-meter Yagi. The operative word here is reproducible. So, to that end, and recognizing that not everybody's junk box contains a Norton bomb sight, I selected this FM Yagi antenna from MCM Electronics. It can be had new for $25, and once purchased becomes the prime parts donor for this project. If you replicate the project exactly as I did, then you will also need 4 440 by 3/4 inch screws with matching nuts and a 26 1/4 inch length of 75 ohm cable. But before you cut that cable, please watch the rest of this video. Now, the main tools needed for the build are a tape measure, a plumber's tube cutter and or hacksaw, a soldering iron, and a drill. And while it's not mandatory, having access to an antenna analyzer will let you confirm as you go that the build is going in the right direction. So, if you don't already own one, let me suggest that building this antenna versus the cost of buying it will make a big down payment on the cost of an analyzer. Okay, that's the setup. Now let's move on and look at what you get for $25. To be honest, I probably fumbled with this box for 3 or 4 minutes, but that was my fault and won't subject you to that. The real point here is to give a general idea of how the antenna comes to your door and what it takes to assemble it. In case you missed it, the answer is not much. While you can't tell it in the unboxing segment, this antenna uses screws rather than rivets, and it's this type of construction technique that makes it a great candidate for this 2-meter conversion project. Now, for those watching who want to know how the 2-meter dimensions were established, this is the route I took. First, I applied the antenna's unmodified dimension to the ARRL's Yagi for Windows software and found that it reported performance numbers that were very close to the manufacturer's specifications. Encouraged by these results, I went on to create models for the 2-meter band. And because I wanted to use the finished antenna in a vertically polarized plane, I needed to move the reflector closer to the driven element so that the boom could be clamped to the mast behind the reflector. To me, that distance was more or less arbitrary, but will confess that I used a spacing suggested in another 2-meter Yagi build. And because I wanted to keep this build simple, I looked at what could be achieved using the boom's original director spacings. After not too many iterations, I found that with these values, the software was predicting good numbers for both the forward gain and front to back ratio. Cutting the reflector and director elements with a tube cutter is straightforward. All I needed to do was subtract the new length from the original length and cut that difference from the ends of the respective elements. So, with just 2 dimensions, 6 end cuts could be made. Okay, that covers the reflector and directors. But how do you shorten the folded dipole element? Well, of course you're free to use any method you're comfortable with, but given my limited metalworking skills, what I settled on was to cut each inside end off by the difference between the out-of-the-box length and the 2-meter length, and then cut twice that length out of the middle using the center mounting screw hole as a reference point. So after making these 3 cuts, I had 2 identical U-shaped pieces that needed to be spliced back together and re-drilled to accept the feed terminal screws. The splice was made by taking a 3-inch length of tubing from a scrap piece of tubing created from any of the earlier cuts. Once I had a 3-inch length, the first thing I did to it was drill a hole in its center big enough to accept the dipole mounting screw. Then I slit the tube lengthwise on just one side. Next, I expanded it so that it would just fit over the 2 dipole tubings. Once the 2 sections are centered in the 3-inch splice, I then drilled 2 holes each side of the center hole, sized to accept the 4 440 by 3/4 screws referenced earlier in the materials list. Okay, we've worked our way through modifying the elements. Now we need to think about connecting the antenna to the radio. The antenna ships with a built-in 4-to-1 balun and a Type F connector for the feed line. And if our radio is just a receiver, we could probably use it without modification. But in this case, the antenna will be used to transmit as much as 50 watts, so a more robust matching network is needed. The modeling software reports that the SWR will be near 1-to-1, but with an impedance that is always on the low side. So even though the free space, folded dipole, and a 4-to-1 balun would look like 75 ohms, the lowering effect of the parasitic elements should work in our favor and allow us to use the more traditional 50 ohm cable. This physical diagram shows us the basics of a coaxial balun, and in our case we know we want to operate this antenna at approximately 146 megahertz. Now let's look again at this equation. It's been simplified to calculate the length needed to form the U-shaped portion of the balun. Earlier I said the 75 ohm cable needed was a 26¼ inch length. The caveat is that this presupposes that the cable's velocity factor is 0.65, but not all 75 ohm coax has the same velocity factor. So this is where you need either the antenna analyzer or have a length of cable with a known set of specifications. And just for reference, here is what I got testing just the coaxial balun with an approximate 300 ohm resistive load. This next sequence of stills shows the steps taken to replace the original transformer balun. Basically, you need to carefully separate the 2 plastic shell halves. Go slow here because they are glued together, but by using a knife and or other thin pry bars that you have, plus some patience, the case should separate without damage into the 2 halves. Then, after removing the circuit board, drill 2 holes that are just large enough to accept the balun cable in the upper case half. Next, after removing the transformer from the circuit board, solder the 2 ends of the balun cable as shown here. Don't forget to solder a jumper wire from the F connector's center trace to one of the 2 antenna terminals. To which one doesn't matter, but one and only one must be connected. Finally, carefully reassemble the circuit board and case halves, and that job is done. Okay, let's stop for a second and recap what's needed to convert this antenna to 2 meters. The 4-to-1 balun has been modified by removing the original transformer and replacing it with a half wavelength of coax, in my case 26¼ inches, but yours may be different due to the velocity factor of your cable. The reflector was modified by cutting 11¼ inches from each tip, and it was physically moved forward on the boom so that it now sits 12¾ inches behind the driver. And to be clear, that is the only boom change spacing needed. The driver, i.e. the folded dipole, was modified by removing 18 inches from the center and 9 inches from each inside tip. Next, each director tip was shortened by 5½ inches. And finally, one of the 5½ inch scrap pieces was cut again to make a 3-inch splice used to put the dipole back together. Okay, now it's time to see how this antenna behaves in the real world. This first test is a single frequency SWR check, with the antenna pointed toward the sky and using a short coax to link it to the analyzer. Under these conditions, the overall SWR reported at 147.5 MHz was approximately 1.5 to 1. Next, with the antenna roof-mounted, vertically polarized, and at the top of an 8-foot mast, this is the analyzer's swept frequency SWR plot looking through 65 feet of LMR 400. For the frequencies from 137.5 to 152.5 MHz. Looking closely, we can see at midband the SWR approaches 1 to 1, and at 147.5 the SWR is approximately 1.7 to 1. So what we know at this point is it could serve as a pretty satisfactory dummy load. But the real question is, does it have any front-to-back ratio? To see how it performs in that arena, we need a steady line-of-sight signal. And to simulate that, I used the analyzer as a source and placed it approximately 150 feet from the antenna. Then, back at the station, I tuned HD SDR to the analyzer's frequency. Watch the S-meter as the antenna sweeps a 360-degree circle. To be clear, it is right at this position of the red line that the antenna is pointing directly at the mailbox containing the analyzer. Now I will reverse the antenna's rotation and observe that the S-meter's response is mirrored that of the first sweep, indicating that the response is repeatable. Well, that's it for this time. I hope you enjoyed it and can see that making a 2-meter Yagi is within your reach. And finally, good luck with your next project. I hope you have as much fun with it as I had with this one.